Today I'm going to present an open source tool that provides statistical and quantitative description of blood traces or bloodstain pattern, as we want to call it. So I do not attend the IAI conference regularly. I rather go to fluid dynamics engineering conferences or the conferences of the International Association of Bloodstain Pattern Analysts. So I'm gonna act like you never meet me. I'm an engineer and scientist. I have expertise in fluid dynamics. I did a PhD on the impact of drops. And then I got interested in this forensic discipline that is called bloodstain pattern analysis. When I was a faculty member between 2009 and 2020, I have served as the lead scientific investigator for 3 research projects on bloodstain pattern analysis, some funded by the US National Institute of Justice, and we have a representative here with Greg Dutton, and also the Army Research Office. I've also performed a BPA in actual crime scenes or on the basis of investigative photographs. I've published scholarly work on forensic and fluid dynamics, and I've served as reviewer for federal agencies on awarding grants in the field of forensics, also looking at forensic standards. My other domain of expertise, I have a couple of hobbies. One is continuous winemaking with nanotechnologies, and the other is the physics of boiling for energy technologies. So this is also related to fluid dynamics, but more happy topics. So without further ado, this is what I want to discuss today. So I'll tell you why I wrote this piece of software, why I wanted it to be open source, what it means to be open source, that everybody can look at it and use it for free. I'll show you the workflow, how the software works, so what you need to provide as an input and what you get as outputs. I'll speak of pre-processing the images because you probably know as practitioners that we don't always get the perfect picture that we would get in an experiment, right? When you go to a scene, sometimes you have to look at all pictures, and that brings significant challenges for the discipline. Then we look under the hood. What is the technology? We'll try to characterize the accuracy and performance. And I'll give 4 examples where I think this tool can be useful to BPA. So many of you have more expertise than me in casework, so I really expect vigorous feedback that you tell me, yeah, that's useless, but maybe this could be useful, okay? And then I'll show you how to download it, and I'll give my contact info. So why did I get interested in this? Well, it's relatively simple. If you hit blood, let's say with a bullet for a gunshot backspatter or with a hammer, you can produce in one hit up to 10,000 stains. And here is some work by Rossi in 2018, JFS, where they counted, and in a semi-automatic way, up to 3,000 stains per spatter. They were producing backspatter by shooting with a rifle at sponge filled with blood, and even a cadaver that they would religiously refill with blood. Down here, it's a heavier version of me with a research team that I was leading at Iowa State University. We've produced a data set of gunshot backspatter patterns that is freely available for download. I'll show the full link at the end, so you can test your reconstruction methods with this data set. And we counted more than 40,000 stains with just one bullet. So the quick answer is you don't want to count these by hand, right? It would be nice to have a tool. And the tool, I'll show you, it can do much more than just count those stains. It can measure those stains. In terms of design, what would be nice is that the tool can run on multiple platforms, right? You can use it on a Mac, on a PC, on a Linux stuff. You can run it from the web, maybe at some point run it from your cell phone. It's nice to have a tool that is free, that you don't have to pay for, because I know that police departments, they are tied with costs, and also something that is dear to my heart is that I teach every year BPA at the University of the West Indies in Kingston. Here I am with my students this spring, and I wanted to do something for them. And since some of the development work had been done with proprietary software using the money from the National Institute of Justice, it was not a huge effort for me to try to convert this proprietary tool into something that is open source. Of course, we want something that is reliable and reasonably fast, so I'll show you some figures of merit. So the work that had been done with government grant in the US, it was a set of scripts, so a series of commands using the MATLAB programming language. And MATLAB is a tool that is used for scientific computing. It's regularly taught in schools of engineering and physics. It's very fast, but it's proprietary. It can cost you up to $10,000, depending the add-ons, the toolboxes that you buy. And there's a version of MATLAB that is called Octave. So it's a different software, but it's 95% compatible with MATLAB. That is a little bit less fast, but still quite fast. And it's open source instead of being proprietary. So open source simply means that the source code is freely available for anybody to do possible modifications and redistribution. You don't have to pay for it, and you can look under the hood, which is very useful if you go testifying, because you don't want to testify with a tool that you don't know, right? So it's free to get. It's not very widely used. MATLAB is used by more people, but like I say, it's very expensive. MATLAB has better graphic capabilities than Octave, so I had to tweak a couple of things to produce the results I'll show you. The support is, you pay for support in MATLAB. With Octave, you can use some of the support material that is available online for MATLAB, or you can ask the community of users. So let me show you the workflow. So what do you need to provide to the code? Here is a blood spatter pattern that was photographed in Jamaica during one of the teaching lab that I was giving. And you can have the labels you want. You need to have a scale, because the tool is going to measure, and without a scale, you cannot measure. And that's your basic input. I'll come back to this later. And then the output. Well, in order to produce the output, the tool comes with a README file. So it's a set of comments and instructions on how to use the tool. I'm not promising that it's super easy to use and it works right out of the box, but I wrote an extensive documentation on how to use this. So the workflow to run these Octave scripts is relatively simple. After you have installed Octave on your computer, according to the instruction in the README file, the first step is to fill a spreadsheet, a CSV file, where you mention the name of the image file that you want to process, the scale in pixel per centimeter, and the path, so the location of that file on your computer. And the software works with queues. That means you can indicate tens of images to be processed while you do other things. The second step is to open the Octave software, where you have a command window, and you can enter the name of the scripts that you want to run. So the first script to run is process images. It's the script that will count and measure the stain. And so you just type that in the command window,
and you hit return, and the processing occurs. Next step of the workflow is to describe quantitatively those files by making those plots and histograms. So first you fill in another spreadsheet the name of the files that you want to describe quantitatively, and again you can have as many files as you want. They will be described sequentially. Step 4, in the Octave command window, you just type describe quant, which is the name of the script that will produce the plots, the histograms, and also the reports, the text reports. And you hit return, and these plots and images will be processed. And they will be stored in the folder images in the form of text report, plots, and histogram, so in the form of images that you can easily recover and download from there. Some of you might not want to install Octave on their work computer. Maybe your agency prevents that. So in that case, there are two possible solutions that I can envision. The first one is that you run the Octave scripts online. There are services that you can purchase online which allow to run Octave scripts. One is at the website cocalc.com, and for a fee that is affordable, it's between $5 and $20 a month, you could install the tool on cocalc.com and run from there. Another possibility, if there's interest, is that my company could set up an internet server where you drop the files over the internet, for example, and they are processed on a server in my company, and then they are sent back to you over the internet, for example, per email or per file transfer protocol, so that you receive the results of the computation, the histograms and the reports and the images of the various plots that are the output of the software. So these are two solutions that are possible.
What is the output? The output is a series of pictures where you have your results. So the first results that I was interested to plot is a histogram. So on the horizontal axis, you have the size of the stains, and here precisely we measure the width of the stain, because it doesn't depend on the impact angle, just on the impact velocity and the size of the drop. And we group, so the software groups the stains into bins. So you see the first bin is the highest, and it has the stains between about 0 millimeter and 0.3 millimeter. So this spatter has a preponderance of stains that are in that range of size. And the vertical axis is the probability density, but it could also be the number of stains. You get two plots. So what this vertical bar here tells us is that the area of that bin corresponds to the proportion of the stains that are in that size range with respect to the total area of the histogram. So that's what the histogram is. And I didn't program this. I used something that was open source, programmed by Jonathan Lancey. He calls this nhist for nice histograms. So it's very powerful. You can plot several histograms on top of each other, compare stuff. So that's one of the outputs. Another output is that it returns the image to you with fitted ellipses around the stains that are measured. And not only that, but it gives you a nice little arrow that points towards the tail of the ellipse that shows the directionality, so the direction of the impact. So here the drop came from the bottom and went up. So that's one of the outputs, and it's on the original image. It superposes those ellipses. I'll tell you later how they are made. Here also there are ellipses, but it's for a bigger picture with more stains. Then it produced plots where you have as x and y the area of your picture, And then the color simply means how many stains you have per unit area. So if it's white or red, you have many stains. So that's here that the action is happening. And in the black region, there are not many stains. Another type of output that I have is also a map, but this map has the average of the aspect ratio of the stains. So if it's dark, you're going to have an aspect ratio of the ellipse that is close to 1. That means the stain is relatively round. And the lighter it gets, the more elongated the ellipse is. And that is something you can use to kind of determine where the blood came from. So that's what I call the aspect ratio, and it is almost directly correlated with the angle of impact. So if you have an aspect ratio of 1, the angle of impact is normal to the wall. You have to write reports, so that thing does it for you. It outputs a text file that you can copy-paste in your reports, where it reminds you what figures you have measured, what is the size of the scale bar, what is the number of spots and stains that have been identified. I'll come to the difference between spots and stains in a few seconds. And it explains also what the histogram is about. There's also a bar that I didn't describe on top of the histogram that describes the average of your measurement and the standard deviation. Now let's take a step back and come back to the exact output that you want to give to the code. Like I say, if you feed a regular crime scene picture that is blurry and underexposed, it's not going to like that. It's not even going to run. So what I had to resort to is a process where we do pre-processing of the images. See, that's a crime scene picture. So that's a wall at the center of a rotating stairway. And you have a bunch of small stains in this area. And you have some proprietary info. So those markers, they have number of the evidence. You have the geometry of the room in the house where the crime happened. It's a big file, it's 20 meg, because it was taken with a professional DSLR camera. And also, there are darker region and whiter region that have nothing to do with stains, right? There are other colors, like the gray of the stairs. So what you need to do before submitting the data to the software, you need to work on that picture to threshold that picture so that you give to the software a picture where the black regions are the stains and the white region is anything else. And the best tools to do that is not to get a new software, is to use what has been proven and used for decades by our community. So you might be familiar with Photoshop. It's really good to extract features from or objects from a background. But here, since we are talking open source, we could work with GIMP or ImageJ, that is newly called Fiji, and that's also a software that was paid by the US government. And doing that, you can erase the black region that is between the stairs, the two boards of wood. You can remove the scale after having measured that scale and written down the values. And you can extract the stains from the background. So here it was relatively easy because the background is white and the stains are red, but those tools are really good. If you have a green background and red stains, you can change the color channels and things like that. And once you've done that, you're left with a picture that is thresholded. So again, it's a black and white picture. In black, you have only the blood traces. The size of that picture is 100 times smaller, in this case, than the original picture, so it's going to be processed faster. And that picture has no link to the scene, right? Maybe you're adventurous enough to send it to a website in California, and nobody's going to blame you, because I don't see the stairs, I don't see the markers on this picture, I just see bloodstains, right? And then that's the real input of my code. And then there's a spreadsheet where you simply write the list of the pictures you want to process and the scale of these pictures. And you can write many so that the software will process maybe 100 pictures overnight while you go to other activities. So it can work in batch also. Okay, so what's under the hood? Because you don't want to get a lousy software that produces random results, right? So once it's fed with a thresholded picture, it applies automatic image processing methods, and especially an algorithm called region props that is very similar to the one in MATLAB. It's an algorithm that has been used by generations of scientists and engineers for counting blood cells, rice grains, fibers. It has been also used for bloodstains in my group and in other groups. And what it does, it's going to identify regions on the black and white image that are groups of contiguous pixels, so neighboring pixels, that are all the same color, typically white or black, and disconnected from the other regions or the other groups. So here you see 9 or 11 regions that have been identified by region props. And that's called the segmentation. And then region props can compute several properties of these regions, like the location of their center of gravity, it's called technically the centroid, their area, and also it can fit ellipses. So you see here a gray region and a red ellipse. So the way it works, it's by a physical argument based on the equivalence of the second moment of inertia between the ellipse and the region that has been identified. Imagine that you would rotate this ellipse along the two main axes of the ellipse. You would need the same energy as when you rotate the original region. So that's how the ellipse is fitted. And for a shape like this, it's not possible to perfectly fit an ellipse because it's not an ellipse. So what I found is that, and it's also well known in the community, is that if you have tails, the second moment fitting of region props tends to make ellipses that are a bit too long. So I also implemented in the code another way to fit ellipses by the least square method of this group, where basically you extract the points of the boundary of your segmented area, and then you try to fit an ellipse to this boundary. And since we already had an ellipse fitted by region props, I was able to cut the tail and also find the direction of the tail and tell the algorithm to focus on the points that are on the other side, because the other side is the one where you have the nicer correspondence to an ellipse. And so the result, you get a relatively better ellipse and also an arrow that points towards the tail that you can use for other purposes. I told you that not all the spots that were spotted by region props were used for making ellipses and counting stains. So there are two criteria that I implemented in the code, but since it's open source, you can put your own. I removed the spots that are very small, close to the resolution of the picture, because we don't know if it's noise or dust or whatever. And also, I fit the smallest convex shape around the stain. And if it has too much difference between that shape and the shape of the stains, I don't count those as stains. So that removes stains that have a larger area that is empty inside, or stains that have weird tails like this. It's not perfect, but the code comes with an open source license. So it's not because it's open source that you can do anything with it. So you cannot take it and sell it saying it's your product and make a lot of profit with it. So every time you redistribute the source code, you need to acknowledge the work of the people who have provided stuff. And that's something that I did also in this software, because I used other contributions from the open source community. And you cannot use my name to endorse your products, or you have to ask me. And also there's a liability limitation. So if something goes wrong with the code, I don't want to eat beans for the rest of my life. So that's what the license says, and it's plainly open, right? So how accurate and fast is that? So I looked first to estimate the accuracy. I didn't spend much time, but I opened textbooks of BPA, like the one of McDonald that has a bunch of pictures of stains with he has given the impact angle. And then Paul Kish, who also wrote a textbook on BPA, he has done similar things. So I produced a file with all those pictures. The impact angle was known. I also used the dataset by Basu. He worked with somebody you might know, Silke Brødbæk, and they produced a dataset of stains also on rough surfaces, because it's harder to estimate the impact angle on rough surfaces. So look at this. And then I used the code to extract the impact angle. So you see here the ellipses fitted, and the numbers are the impact angles. And then I compared those numbers to the ones that are provided in the literature. And we get an average error that is between 3.9 degrees and a bit more than 6 degrees, using either the region prop algorithm or the ellipse fitting algorithm. The ellipse fitting is a little bit better, and what also makes the accuracy better is if you don't try to fit ellipses on stains that impacted normally, so at values close to 90 degrees, because those are never completely round and you have the largest errors there. And you can see that the error that is reported by my code is close to other measurements that have been, other estimates of the error that have been done, for example, by Joris using the ellipse fitting model, where he also had errors that were up to 4 degrees. So that's something to know. And I always say it's not important to have something perfect, because in this world we have nothing perfect. But what matters is to know the uncertainty and of your measurement. So it's here. In terms of speed, I processed various pictures, and then I recorded the computational time in minutes. So that's the horizontal axis, and vertically are the number of stains that are found. So it goes smoothly to 25,000 stains, which is quite a lot. On casework, you're probably never going to have that many. And it processes about 1,700 stains per minute. So that's a bit faster than the average BPA analyst with a ruler and things. That was done on this computer, which is mid-range processor now. It was great when I bought it 3 years ago. It has a lot of RAM, 48 gig of RAM. Octave is not great at managing the memory, so remember to get a lot of RAM if you do big pictures with a lot of stains. Okay, so here comes the interesting thing. So is this relevant and useful for BPA? So I'll show you 4 examples, and then you'll hit me on what you think. The first warning is that this is not about replacing the analyst or the BPA researcher. You still need a scientific mind to formulate your hypothesis and to test them. It's just going to help you to test your hypothesis, and it's going to count the stains for you. So let's look at classification. So many of you know the textbook of Bevel and Gardner, and they have a decision map where you go along a decision tree and you have to answer questions by yes or no. And my claim is that some of these questions, they might be assisted by this tool, so that you can get an answer that is less, that is more quantitative, and that is, people will agree, because sometimes it's hard when you have several people to agree on questions like this. Are the stains only small circles or ellipse without flow? If you have 40,000 stains, have you looked at those 40,000? It's hard to answer these. Or the diameter of the stain is between 0.1 and 3 millimeters. So that's not from Bevel and Gardner, that's from another classification map that I've been using. Again, how do you answer this question if you have many, many stains? Then is the distribution, the spatial distribution linear or curvilinear? That's something you could answer. Do you have a progressive change in shape? What does progressive mean? Can you measure that? Do we have a radiating distribution? If you do impact spatter pattern, you understand the importance of this question and also the difficulty of practically answering it. And also satellites of spines. So the first answer about measuring stain size, well, it's very easy. If you have a histogram, then you can just integrate the curve here between your two bounds, here 0.1 and 3 millimeter, and you get a percentage. You get 60% of the stain. So good enough, I don't know, but then you can make quantitative decisions that are less arbitrary than trying to answer this without quantitative measurement. The progressive change in shape, remember, you can have aspect ratio map. So that's the aspect ratio is simply the ratio of the length and the width of your ellipse, which is a proxy for the shape. And here you can easily extract, numerically even, how progressive your change in shape is. So if you have a very fast or a narrow gap between the black and the yellow, or the light red, then it's very sudden decrease or change in shape. But if everything is the same color, then you have no progressive change in shape, but at least it's measured. You can, so that's all for classification. I could show some stuff with artificial intelligence if you're interested, but I want to show you something about quality control now. Let's say you prepare a class for BPA, you BPA people, or you prepare an experiment for casework, where you hit with a hammer a pool of blood and you produce spatter patterns, right? Well, if you want to be accurate and if you want to make your life easier to test hypotheses, you better have a repeatable way to hit with the hammer. But it's hard to know, right? Because you would need a high-speed camera and you would need to move the hammer exactly the same way each time. So one proxy for figuring out if your experiment is repeatable is to look at the stains. But again, it's hard. If you have 40,000 stains, how do you compare two spatter? They look about the same, right? Well, just plot a histogram. So that's what we did for an experiment where we did 3 impact spatter patterns. And you can see here that the 3 curves, they're almost impossible to distinguish. They have the color black, brown, and yellow. And those bars on top, again, they show the average, which is pretty much the same between the 3 experiments, and the standard deviation. So with this data, you can get a feeling that your stuff is repeatable, and you can move on to more important things. And if it's not repeatable, it's going to show. Okay, so a third use that I'm happy to report is that you can use this to test hypotheses, for example, on the physical basis of BPA. And the older generation among us might remember those very bitter arguments between members of the IABPA about what is the physical variable that controls the size of stains when you have a blood spatter pattern. There was McDonnell who started in the 70s by saying that the diameter of the spatter stains, they are mainly related to the velocity of the impact. And by velocity of the impact, I mean the velocity of the object that is impacting the pool of blood and creating the spatter, okay? Not the velocity of the drop themselves. There's a lot of confusion about this. And he came up with this very criticized terminology of high velocity, medium velocity, and low velocity spatter, right? Then Bevel and Gardner, they came and they put out the theory that the main variable that determines the stain size is the energy of the impact. And later they also mentioned that the force of the impact is the main variable that controls the drop size. So again, we're talking of the energy of the material of the object that impacts the blood drops, not the energy of the drops. With my physical background, I'm confused here because I know that the velocity is not the same as the energy or the force. They are measured with different units. So can we design an experiment where we would try to resolve this controversy? So we did, actually. We used two different impactors that were released from the same height so that they hit at the same velocity a pool of blood. But one was very light, made of plastic. The other was heavier, made of steel. Let's say it had a mass that was 10 times the mass of the plastic one. And we end up with spatter patterns that are produced under condition of same velocity, because the velocity only depends on the height, but different energy, because the energy depends on the mass also of the impactor, and the steel impactor was heavier. And boy, it's complicated. So that's a member of my team that did a high-speed movie, and we published a few papers on the mechanisms of atomization. First, you break the blood into pieces, and then as it flies through the air, it breaks to even smaller pieces, and so on and so forth. And you see the special configuration of this sheet that breaks. It's really amazing. So you have breakup from the pool of blood into 2D sheets, and then 1D jets or rivulets, and then they break up into 0D points that are the drops themselves. And in order to make our experiment repeatable and get nice comparison with the histogram, there was a guiding rod, and the stains that were collected around that in a cylinder that was lined with paper. Our impactor was a little bit round. Here I showed you again already that our process was repeatable, which was very important for our purpose. And then we got results. So the algorithm, the tool that I'm presenting today, counted those stains and also produced a representation of the average stain size for every experiment that we are doing. So it was extracting a representative stain size from those thousands of stains that were generated at each experiment. And we did about 30 experiments. So that's the horizontal axis in this log-log plot. And then we plotted, that's with Ricky Faflak, who was working in my team at the time, the impact energy in red and the impact velocity in blue. And try to judge which one of these two quantities is well correlated with the size of the stains. It's the blue, because they all fall on that straight lines. And it's a log-log plot, so that's very often used by physicists. That means there's a power law relationship between the velocity and the diameter of the drop. We did also some other measurements, not just the size of the drop, but their position, the average height on the paper. And again, the correlation is much better for the velocity than for the energy of the impact. So what it means is that the primary variable that controls the stain size in impact spatter pattern is the velocity, not the energy. So remember that when you testify in court, right? Also, something I want to say is that that's not the whole story. So if you go to this fluid dynamics journal, you'll see pretty heavy mathematics and also some experiments that show that in some circumstances, both the velocity and the energy, they contribute to the size of the stain. So I'm not telling you the whole story, but hopefully somebody is going to read this and cite it, because it's been lying unknown for a long time. And that, to me, that's a testimony that our community doesn't interact enough with physicists and fluid dynamics scientists. The last thing I want to show you is the possibility of using this tool to determine areas of convergence or origin. That's something that is not implemented yet in the stuff that I put online, but basically you can plot functions of the orientation angle, the directionality if you want, and if you know your trigonometry well, you can have on your plot very strong color differences at the location where you have the height of the source of blood and the left-right position of the source of blood. You see, each time you have a contrast between a dark region and a light region. And what I have plotted, those lines here, are the known location of the impact location. So it seems to work reasonably well for impacts that are close to a wall, and for good reason I could explain you. So that obviously, if you have a tool that allows you to fit ellipses, you can start to determine impact angle and use it for reconstruction, even though this is not exactly super important for many casework. It's more important to determine what was the physical reason for those stains that you see. So that's what I wanted to show you with the code. It kind of fits with my philosophy about research and development. When I look at a problem, I always try to see if I can add some more physics. So in BPA, many times there's some physics that is neglected, and I've done a lot of work to add more fluid dynamics to BPA, and that's more an academic goal. But also, I strongly believe that if you want to present things in court, it's better if your argument is supported by some quantitative evidence than just your feeling or your impression as a BPA analyst. So I'm trying to move the field from a qualitative perspective to a quantitative perspective. And I hope this software goes into that direction. And that is going to help both for testimony in court, but also that might provide better tools for doing investigations. So now, where do you get that thing, that software? It's on GitHub. So that's the link that you need to hit in order to download and test the software. And you can, hopefully you're going to contact me and say, yeah, this is not working, we need to fix this, how about we do this? I'm not running a giant factory, so I'll respond as I can. Remember, it's free, so you don't owe me, you don't own me, right? But I really look forward, and I hope maybe somebody from the audience has an interest to push the boundaries of this towards more usability or a different language or integration with your cell phone, whatever. I'm interested. And again, I got some federal money when I worked as a faculty member to develop some of these tools. They were in a proprietary language called MATLAB. And now I'm really happy to be able to share this back with the community in a form that is open source. So the conclusions, I presented an open source tools. It's written in an open source computing language called Octave. It counts the stains, it fits ellipses, it produces histograms, maps of spatial densities, aspect ratio. You can run it on your own computer or online. It can also compare several histograms. You can put 100 histograms on top of each other, but then you're not going to see anything. So pick and choose, right? I presented 4 applications. I want to acknowledge what I just said, that some of it was paid earlier by US government agencies. Also, the work was done in team, so at least at the beginning of the development of the software in MATLAB. And these are papers from from research that I led, and the students or researchers in black, they have contributed to some extent to the development of the tool in MATLAB, and the transition to open source Octave is my job. So I'm the only one to blame if the code doesn't work on Octave. There are other teams that have worked on comparable technology, so I've cited here their work. Again, this is the link to download the tool. My contact information, and here another link to my publications. And now we have hopefully some time to think about this, and I would be pleased to hear about your impressions or your feedback on this tool.
Thank you.